Hey there, welcome to another episode of At the Workbench at 4111 Spyglass. Last week we left off with the two radio nodes having separate roles, one only transmitted, one only received. The two nodes shared the code for setting up the radio, but had different modules or state machines to transmit and receive. It was trivial to merge the codes. The only new element required was a radio arbiter that shifts control of the radio between the transmit and the receiver function. Loading this combined firmware onto the nodes, I found that they were, let's just say, temperamental. One of them was transmitting and receiving just fine. The other, mostly transmitting and dropping nearly all received packages, even though they ran the same firmware and they were fed at the same rate. Even the well-behaved node dropped way too many packages. The arbiter itself was fighting me. Originally, our system had three separate state machines, one for USB input and transmit, one for receive and USB output, plus an arbiter that decided who owned the state machine at any time. Altogether, we had 10 states. I won't even attempt to show how and when they transition. The worst part? These states are similar but not identical. For example, each machine has an idle state. One machine's idle is another machine's operate. Plus it is difficult to analyze and debug. That's how you get race conditions that only show up at high packet rates. At low packet rates everything looked fine, but once we pushed the packet size or the rate, things fell apart. One node would get stuck in transmit. Receive would get interrupted mid-packet and packets were dropping everywhere. And here's the weird part. Two identical nodes, same firmware, same packet rate, but one behaved like a half-duplex or simplex jump, while the other collapsed into a transmit-heavy, receive-starved mess. We quickly identified the issue. Transmit was allowed to preempt receive. A filling USB buffer or a timeout on receiving USB bytes triggered transmission even if the radio was receiving a packet. At slow rates and with short packets, the receiver might finish its task. At faster rates or for larger packets, most packets were truncated by the radio being forced to switch to transmission. The issue was quickly resolved by changing the arbiter policy to forbid abandoning receive in the middle of a packet. But we still lost 10% of packets along the way. 10% loss is unacceptable, given that we had 10 states in combined state machines. Chasing down glitches and delays made me question my life choices. There were simply too many ways for the system to act up. So I threw the whole thing out. Instead of two state machines and an arbiter, I rewrote the entire radio layer as one unified state machine with just 5 states. INIT. RX listening, RX processing, TX start, TX wait end. That's it, and suddenly everything behaved. With the new architecture, both nodes can send and receive 61-byte packets at 100 millisecond intervals without stepping on each other. RX always wins. TX can only start when the air is clear. And if anything weird happens, overflow, underflow, partial packet, mark state glitch, we collapse everything into one recovery path and restart the machine. These changes encoded in just 5 states governing transmission, reception and USB input-output reduced the drop rate from 10% to essentially 0, meeting our requirement of robust and reliable communication. Since we now have a robust setup, I used the opportunity to clean up the code according to some clean code principles. Single Responsibility Principle or SRP. A function or class should do one thing and have only one reason to change. Let me show you the new CC1101 driver or class. I am taking advantage of the C++ templates to compose classes or to inject one class into another. This is the driver I always wanted, minimal, predictable and impossible to misuse. It implements the reset sequence recommended by Texas Instruments, configures the radio for 432.4 MHz at 38.4 kilobits per second, enables widening in CRC, and exposes a tiny API. Strobe commands, register read-writes, burst buffer transfers, and transmission power control. That's all you need. And for each of these we create a data type that clearly specifies the allowable registers. Whenever possible, we should let the compiler check arguments and parameters. And here's the manager. one ring buffer for USB data, one RF packet buffer, one USB TX buffer, and a single process loop that handles everything. RX gets priority. TX can only start when the channel is clear, and force RX is the universal recovery path that puts the radio back into a known good state. This is the first time the CC1101 feels like a well-behaved peripheral for me, instead of a gremlin finding me at every step. Now that the firmware is stable, let's take one node for a walk and see how far we can get. We plug one node into the server and place it in the window. The other node is plugged into the laptop, and we can take it outside to see how far we can reach. Okay, so we're standing now outside the window where you may see the antenna or the transmitter happily kind of flashing away. Yeah, we're doing well, about 70 dB, and the packets are coming in nicely. So let's hike away. Yeah, packets are still coming in. That's where we are standing before. And that's where we are, and the packets are still rolling in nicely. Okay, let's go a little bit further and see. 91, 92, 93. Oh, I missed one. 97, 8, 9. Okay, they're still coming. We are at about 70 dB. So things are working nicely. That's where we're standing before. Well, we're still receiving. It's not quite the promised 500 meters, but let's keep going and see whether we can get a few more meters in here. Now both antennas are terrible, so I'm not expecting miracles, but that's part of the fun. Thanks for watching this episode of At the Workbench at 4111 Spyglass. Both the naive merge of last week's receiver and transmitter codes as well as the robust rewrite are available on GitHub. See you around!